Hello everyone, I'm Norman Wahlberger and welcome to the Algebraic Calculus. In today's video we're going to touch base with the oldest calculation in calculus that involves curves, a very famous result from antiquity due to Archimedes, and it's intimately associated with this beautiful curve called the parabola, which will figure very prominently in our development of calculus. And we're going to use the language and the terminology and the notation of these oriented polygonal splines that we talked about last time. Okay, so the object of interest today is the parabola, which is arguably the simplest curve after the straight line. It has the quadratic equation y equals x squared. So a pretty simple equation. And here is the very familiar graph y equals x squared. And I've plotted a few points, 1, 1, 2, 4, 3, 9, minus 1, 1, minus 2, 4, etc. This will be very familiar to students of high school. Okay, so this was studied by the Greek mathematicians, notably the great geometer Apollonius and then also Archimedes, around 200, 250 BC. But they didn't study it in this Cartesian framework with coordinates. They studied it rather geometrically as a conic section, and we're going to talk more about conic sections more generally in a later lecture. But for us, we're looking at it from this Cartesian point of view, and the crucial thing is that this parabola has a parametrization. That means that we can systematically describe the points which lie on the parabola through this simple parametric equation, t comma t squared. So for every value of t, you plug t in there, you get a point on the parabola, and correspondingly every point on the parabola is of this form for some t. It's called a parametrization of this curve, even though we actually haven't defined what a curve is officially yet. Okay, so we're going to use this and we're going to study this parabola. We're going to look at some very interesting questions about how to define areas associated to this parabola. And we're going to work with our spline notation and signed areas. So along the way, we're going to be doing some calculations in this lecture. And actually, I'm going to be framing the calculations and leaving a lot of the details of the development to our worked problems in the actual course proper. So there's going to be some things for you to be doing and looking at and studying aside from just these videos. Okay, so there's actually quite a few things to do in this lecture today. We're going to be quite busy. Now, although we've written down a parametrization for the curve, in practice, we actually can't get at all of the points on the curve. The parameter values are including numbers which are getting bigger and bigger and bigger and eventually beyond our computational abilities to deal with. So it's wrong for us to think that we're capturing all of the points. It's too grandiose a kind of an aspiration. But what we can do is we can aspire to getting at precise points and looking at linear approximations to the curve. That's a good first approximation to what the curve actually looks like. In fact, it's quite close to what computers do when they're graphing curves. So let's look at parabolic splines. And the simple kind of motivation is when we look at, say, something like this. We look at a few points on the curve, say A0, which is 0, 0, A1, which is 1, 1, A2, which is 2, 4, and A3, which is 3, 9. So let's just look at these 4 points. So they're all points of the form k comma k squared. We're now restricting ourselves to k being an integer value here. So these points all lie on the parabola y equals x squared, of course. And we can create a spline. We can create a spline by just joining them up with linear segments. Now this will not be the same as the curve, of course, but it will be an approximation to it. So we might want to estimate what the signed area of this OPS is. So there's the OPS, A0, A1, A2, A3, this oriented polygonal spline that starts here, and then here, and then here, and then here. And we know what that means. Well, first of all, it refers to a signed area that we get by starting at this point and ending at this point and going back to the origin. It's the signed area of this segment. And in terms of our definition, it's the signed area of the first oriented edge, A0, A1, and then the second one, A1, A2, and then the third one, A2, A3. And because this is not a cyclic OPS, we're not going back here, we're just looking at the sum of these three signed areas, which geometrically is going to give us exactly this shaded region that we've got here. Okay, so we know how to do this. It's quite familiar by now. Calculating signed areas of segments just means taking our fundamental definition of the signed area. So here's 0, 0, here's 1, 1. We take 0 times 1 minus 0 times 1, that's 0 minus 0 all over 2. And then the next segment, 1 times 4 minus 1 times 2, so that's 4 minus 2 all over 2. And the next segment, 2 times 9 minus 4 times 3 all over 2. And we get a total of 0 plus 1 plus 3 for a total of 4. All right, that's very nice. So we've got the signed area of this OPS, which is a kind of integral approximation to a part of the curve y equals x squared. Now, as we go through the course, we like to make specific computations, but we also want to look towards a little bit more general computations that shed a little bit more light on the pattern of what's going on. And let me illustrate that here by replacing that specific spline that we just looked at with a more general spline, but still really in the same direction. So instead of just going up from A0 up to A3, let's go from A0 up to AN, where n is some positive integer, natural number, but it's not specified which one exactly. So we're still talking about things with the form a sub k, k squared, where k is in this case a positive integer. And we're going to look at this spline A0, A1 up to AN. A0, A1, A2, A3, A4, up to AN, whatever AN is. And the one just before AN will be AN minus 1. Okay, so what's the signed area of such an OPS? Well, it's going to be the sum of the signed areas of all its oriented edges. So S of A0, A1, and then S of A1, A2, plus S of A2, A3, etc., all included there, till the final one, S of AN minus 1, AN. Sum of all the oriented edges of this thing. So now we have to get at what does a typical oriented edge look like and what's its signed area. So let's look at, rather than a specific value, let's look at a general value. Let's look at a sub k minus 1, which is k minus 1 and k minus 1 squared, together with a sub k, which is k squared. So we're looking at it now from the point of view of having this variable index k instead of a specific index. So what is the signed area of this oriented edge? Well, we can do the same thing. It's k minus 1 times k squared minus k minus 1 squared times k, all divided by 2. Okay, so when we look at this, there's a k minus 1 that's common, and there's a k that's common. So we can pull that out, and there's a 2 on the denominator that's also common. And what will we have left if we pulled out those common factors? Here there would be a k left over, and here there would be a k minus 1 left over, and we have to take the difference of those. So k minus k minus 1, that's just 1. So that doesn't appear. So this thing simplifies to just k minus 1 times k over 2. And this is a very special kind of number. It's a binomial coefficient, k choose 2, and it's a triangular number. So the signed area of one of our little oriented edges in this pattern of points lying on our quadratic curve with integral values, these numbers are triangular numbers that we're getting. So here's our formula for triangular numbers. N choose 2, which is n minus 1 times n over 2. And here are the values of these things. So here's values of n from 1 to 10, and here are the corresponding triangular numbers n choose 2. So when n is 1, we get 0. When n is 2, we get 1, and then we get 3, and then 6, and then 10, 15, 21, 28, 36, and 45, and so on. And they're called triangular numbers for an obvious reason. If you look at this little diagram here, this is the case when n equals 5. There's 10 of them altogether. And you can see 10 balls or circles arranged in a triangular kind of pattern with 4 on the bottom and then 3 on top of those, and then 2 on top of those, and then 1 at the very top. So it's 1 plus 2 plus 3 plus 4. That's another way of thinking about what this triangular number is. And that total is 10. And notice also that to go from one of these entries to the next one, we can do it relatively simply. To get the 15, we can just take 10 plus 5, and that gives us the 15. And to get the 21, we're just adding 6 to the 15. And then here we add 7 to the 21, and so on. This is a very famous sequence going back to the ancient Greeks, who were very interested in the geometry of these numbers. They thought they were very pleasant numbers, which they are. And in Sloan's online encyclopedia of integer sequences, this is a sequence with number A000217. All right, so these are the numbers that appeared as the signed areas of our oriented edges in our polygonal spline approximating y equals x squared. And so we can now finish our calculation. The signed area of this spline A0, A1 up to AN will be the sum of all these oriented edges and their signed areas. And so we're going to get 0 plus 1 plus 3 all the way up to the last one, which is going from AN minus 1 to AN, which is the nth one, n choose 2, or n minus 1 times n over 2. So when we add these things together, when we add the various triangular numbers, then we get new numbers which turn out to be called pyramidal numbers. And the formula for this sum is n minus 1 times n plus 1 over 6. It's quite pleasant, sort of an analog of the triangular situation. Here we're multiplying consecutive numbers and dividing by 2. And here we're multiplying 3 consecutive numbers and dividing by 3 factorial, or 2 times 3. The pyramidal numbers have this number in Sloan's encyclopedia, A000292. And they're called pyramidal numbers because, for example, if you look at the case n equals 5, if you added up the first 5 here, you would get 1 plus 3 is plus 6, that's 10, plus 10 is 20. And that's what you'd get when you stack like cannonballs in a sort of pyramidal array with 10 on the base. And then above the 10, you stack 6, just exactly in the spaces between those ones there. It's sort of space for 6 more to sit on top of that first layer. And then on top of that layer, you could put 3 more. And then on top of that 3, you could put 1 more and you get a nice stack of pyramids of cannonballs with 20 altogether. So 20 would be the case when you have n equals 5. There'd be a 6 here, which would cancel, and then there'd be a 5 times a 4. That would be 20, so that's the 5th pyramidal number. Now notice that this expression could also be written a little bit more simply, perhaps. If we combine the n minus 1 and the n plus 1, we get n squared minus 1. So when we multiply by n, we get n cubed minus n over 6. And that's a cubic expression in n. That's telling us how the signed area of this OPS, this oriented polygonal spline, is growing as the number n increases. As n goes up, the signed area goes up essentially cubically. So it's roughly a polynomial in n of degree 3. And the lower terms are maybe not so significant when you're looking at large values. Now let's have a look at a related but different kind of application of these splines. To not approximate the curve over larger and larger regions, but actually to approximate the curve better and better over a fixed region. So let's look at y equals x squared just between 0 and 1. So it's some kind of arc of the parabola like this. And let's try to get at that arc by subdividing the interval 0, 1, let's say into 4 pieces. So from 0 we go to a quarter, a half, 3/4, and then 1. And we look at the corresponding points, still using our same parametrization. So here we're going to get 1/4 and then 1/4 squared, which is 1/16. Here we're going to get 1/2 and 1/2 squared, which is 1/4. Here 3/4 and its square 9/16. And once we get up to 1, we'll get 1/1. Okay, so now we have these 5 points. That gives us a OPS, which is some kind of approximation to the actual curve over this interval. So let's have a look at the signed area of this associated spline, which is going to be, of course, the sum of the signed areas of its various oriented sides. So A0, A1, plus A1, A2, plus A2, A3, plus A3, A4, the sum of the signed areas of those 1, 2, 3, 4 different oriented edges. Okay, so we can calculate that because we have the coordinates of the points and we just use our basic formula, AD minus BC over 2. So from A0 to A1, we're taking 0 times this plus minus 0 times this over 2. That's going to be 0. From here to here, it's 1/4 times 1/4 minus 1/16 times 1/2. There it is there, over 2. From A2 to A3, going from here to here, it's 1/2 times 9/16, that's 9/32, minus 1/4 times 3/4, which is 3/16, all over 2. And the last one, we get 3/4 times 1 minus 9/16 times 1 all over 2. And you could check that these numbers turn out to be 1/64, 3/64, and 3/32 for a total of 10 over 64, or reduced 5 over 32. And what's that telling us? Well, that's the sum of all the signed areas. So that's the signed area made by this oriented triangle, and this one, and this one, and this one. So altogether, those oriented triangles just fill out this space that I've labeled with the green lines there. So we're getting the area that's determined by the spline and the starting point, which is a kind of polygonal approximation to a portion of the parabola, or an arc of the parabola, the part of the parabola between 0, 0 and 1, 1. It's an approximation to that. So that's a nice calculation. But now we can go further because we can generalize. Okay, so we're going to now stick with the same portion of the parabola, just from 0, 0 to 1, 1. And there it is there. And now we're going to consider a more general subdivision. We're going to now subdivide the interval 0, 1 into n different pieces, all separated by 1 over n. 1 over n, another 1 over n, another 1 over n. So n of these 1 over n pieces altogether. Then correspondingly, we're going to get these points on the parabola where the parameter takes on the values 1 on n, 2 on n, and so on. So A0 will be 0, 0. Then A1 will be 1 over n, comma, 1 over n squared. A2 will be 2 over n, 2 over n squared. So the y-coordinate always has to be the square of the x-coordinate. And then I'm carrying on, and I'm showing you the kth one. So somewhere in here, the general kth one is k over n and its square, k over n squared. And finally, we keep on going until the very last one, when the k actually becomes n, then we just get 1 and 1 squared, so 1, 1. So we're going from 0, 0 to 1, 1, and all of these points are on the curve. They're equally separated along the x direction. And now let's calculate the signed area of one of these oriented edges. Let's say the general one from k minus 1 to k. So s of ak minus 1 ak. What is that? Well, there's the kth one. And the k minus first one is just like that, but there's a k minus 1 instead of the k. So if we take the formula, we have to take the k minus 1 over n, which is the first entry of that previous one, and multiply it by the second entry here, k over n squared. And then we have to subtract the second entry of the k minus 1 fellow, which is k minus 1 over n squared, times the first entry here, which is k over n. That's the AD minus BC applied to these 2 points. and we have to divide by 2. Okay, so what happens? Well, there's some common factors. There's an n and there's an n squared here. There's an n squared and there's n, so there's a common factor of n cubed in the denominator. In the numerator, we have a k minus 1 times a k as a common factor, and we get the same kind of thing as we did before. Here there's a k extra, and here there's a k minus 1 extra, so we get k minus 1 times k over 2n cubed. That's the value of the signed area of one of these little oriented edges. So it's a lot like what we got in that first calculation, but now there's an n cubed also in the bottom. N is the number of intervals that we're assuming we've subdivided 0, 1 into. All right, so in this calculation, the k is like an index that's sort of running from 1 to n. So k could be any value between 0, actually between 1 and n. And for any one of those values, we get a corresponding signed area of the corresponding oriented edge here. So now to find the signed area of the entire spline, we just have to add up all of these signed areas of the oriented edges. Okay, so the signed area of our OPS is the sum of the signed areas of its various oriented edges. And we can introduce summation notation. So this is our first go at some contact with that. We introduce this sigma sign, sum k equals 1 to n, to represent this sum. So instead of having to write it out this way, we just look at what is the typical term and what is the index that's running or that's changing. So we can express things in terms of the index k going from 1 to n. And then the typical term will be s of a sub k minus 1, a sub k. So this sort of compactly represents this sum. And this signed area is just what we computed on the previous page. That was k minus 1 times k over 2n cubed. All right, so this is a compact notation for what's really this sum here. So this thing here is 0, and this first one is 1 over n cubed. That's the case when k was equal to 2. K is 2, we get 2 times 1 over 2, so that's just 1 over n cubed. This is the case when k is 3. We get 3 times 2 over 2, so that's 3. The next one will be, k is 4. It'll be 4 times 3 over 2, so there'll be a 6 there, and so on. And the last one, when k takes the value n, will be n times n minus 1 over 2n cubed. So this is the thing written out in sort of traditional form. This is a compact representation of it. And with the compact representation, we can do things like pull out a common factor. So this n cubed is common to all of these terms. You can see that here as well. We can pull that n cubed out. And then what we have left is just a sum of the triangular numbers, 0, 1, 3, up to n minus 1 times n over 2. So in other words, we're summing k equals 1 to n of k minus 1 times k over 2. That was a triangular number. So we know, in fact, because we've just done it, what the sum of the triangular numbers is from k equals 1 to n. That was a pyramidal number. So we pull the n cubed out, and then we get the sum of the triangular numbers. That's that thing there. And then we can simplify a little bit because one of these n's here will cancel. So we'll have n squared minus 1 in the numerator and 6n squared in the denominator. And then we could pull out the 1 over 6, and then the n squared over n squared will be 1, and then minus 1 over n squared, so we can write it this way here. That's a very nice way of expressing it because it's making it clear now what happens to the signed area of this oriented spline as the number n of subdivisions gets bigger. As the number n of subdivision gets bigger, this quantity 1 over n squared starts getting smaller and smaller, getting closer and closer to 0. And so the total value here is necessarily getting closer and closer to 1/6. So as n gets big, this approaches 1/6. we've kind of done our first calculus computation here. Okay, great. What we've done is we've said that, okay, we look at this part of the parabolic curve. We're going to approximate it with a linear spline, equally spaced with endpoints. We're going to calculate the signed area of that thing, get a very concrete expression for it. Then we look at what happens as the end gets big. We don't have to say it goes to infinity. We can just say, oh, it's getting big. As it gets big, we can all see that this is getting small and this thing is getting closer to 1/6. Nothing mysterious about it. Now that might motivate us to say, aha, that means that the area determined by the curve y equals x squared and this segment is exactly 1/6. But we're not really in a position to say that because we have not yet defined what the area of this thing means. Okay? We're only computing the area of a polygonal spline at this stage, which we know exactly what that means. And we're talking about some kind of limit of that spline as n gets bigger. But we should not make the mistake to suppose that this is somehow calculating a priorly defined area of a parabolic arc. Okay, so let's just make note of that. We do not yet have a definition of a parabolic arc. Nevertheless, when we do have such a definition, we certainly hope that the value in this particular case better be 1/6 because this is intuitively very reasonable. And now I'm going to make another observation. Very famous observation that goes back more than 2,000 years to Archimedes. And it's this observation here, is that if you look at a triangle whose points are O, A, which is 1, 1, and this point B, which is 1/2, 1/4, halfway between our starting and end points, okay, that triangle there, its signed area is easy to find. So if we're looking at triangle OBA in this order here, then we have to take the cross product of 1/2, 1/4 with 1, 1. So that's 1/2 times 1 minus 1/4 times 1. That's a total of a quarter. We divide by 2, we get 1/8. Okay, so the area of this thing here, the signed area of this triangle is 1/8. And we're making the observation that the 1/6, which is our guess as to the area of the parabolic arc, that is 4/3 the signed area of the triangle. That's a true statement. This is 1/8, we can calculate that, and 1/8 times 4/3 is indeed 1/6. So there's a ratio between this parabolic area, the area of the parabolic arc, which we have not entirely defined yet, and this oriented triangle's signed area, which we have defined, and the ratio is this factor 4/3. And that was remarkably discovered by Archimedes, but not just in this case, but actually in a much more general situation. So Archimedes, the greatest mind of antiquity, and possibly the greatest mind of all time, was really the first person to make a calculus computation involving a real curve, which is not linear. So Eudoxus before him had made calculus type computations, and Archimedes made other ones as well, but they were often typically involving linear things like triangles and pyramids and such things. So this computation with the curve was really a brilliant thing. And we can call it Archimedes' Parabolic Area theorem. And so I'm going to frame it this way. So here is a parabola. Now, the ancient Greeks did not think about a parabola as being the graph y equals x squared in the Cartesian framework. They had a rather geometrical understanding of a parabola, and we'll talk about that in a later video. So let's just assume that we have this parabola of Archimedes. And Archimedes would have understood that one of the key things about this parabola is that it has an axis of symmetry. There's this axis right here, which is an axis of symmetry. So there's mirror symmetry here. Okay, so that means that's a kind of a special direction. Okay, and here is his theorem, that if you take a parabolic arc, by that we mean, let's take 2 points on the parabola, say A and C, and let's consider the portion of the parabola between them. Okay? And so the parabolic arc that we're talking about is this region that's determined by this parabola itself between A and C and the straight line joining A and C. So in this picture here, it's sort of denoted by the red lines. Okay, so Archimedes was interested in the area of this thing. So let's suppose that we have an idea of what the area means. His statement is that the area of a parabolic arc is 4/3 the area of the maximal triangle inscribed in it. What do we mean by that? So here's a triangle, ABC. And of all the triangles inscribed in this parabolic arc, so with 2 of its sides being AC, but B possibly being around here, this is the maximal one. It's got maximal area. And that, not too hard to see, that's essentially due to the fact that here, exactly at this point here, the tangent to the parabola at this point is parallel to AC. Okay, so if you go down parallel here, you get to this point. That's sort of the maximal point. Any other point will be on this side of it, and so the in terms of classical definition of area of a triangle, the height will be less. Height, when you think of this as the base, will be less than it is for this value here. So this turns out to be the maximal triangle inscribed in this arc, and Archimedes is saying that the area of the parabolic arc is 4/3 the area of this triangle ABC. So I'm denoting this here with this sort of symbol. The area of the parabolic arc, let's just introduce that temporarily, ABC, that's referring to this whole thing created by the parabola, is 4/3 the area of the triangle ABC. So Archimedes did not talk about signed areas and so on. So this is classical Greek mathematics in terms of standard kinds of areas. But nevertheless, it's really the first place where we get an inkling that we can get at the area of a curved region. Okay, this is hugely important for calculus. Here's this crazy curved region, well, not so crazy, but it's still curved. But Archimedes is telling us exactly what this area is. It's 4/3 the area of this triangle, which we can easily find. We just multiply it by 4/3 and we get the area of this parabolic thing. It's incredible. Okay, it's incredible that such a formula even exists, really, because why should it? So we'll see that the ramifications of this are really very huge. And so we would like to understand this from our point of view, and we are now in a position to do that. But some work is required from us. All right, so to verify Archimedes' theorem, what we can do is we can extend our original computation. So we computed what might be the area of this segment of the parabola from 0, 0 to 1, 1. So the first thing to do is to extend that to, say, from 0, 0 to a general point on the curve, say A prime, which is A comma A squared. And it turns out that we're able to do this, so really the same kind of argument gives us a very similar formula for this area here, this area determined by the parabolic arc from 0, 0 to A squared. And it turns out to be A cubed over 6. So when A is 1, we get the 1/6, but in general, it's A cubed over 6. And that kind of syncs with our earlier computation of the dependence of such a spline area when the n gets big. You remember there was an n cubed kind of thing involved, so we're not surprised that there's an A cubed there. Okay, so once we're in possession of such a formula, which we could get at by generalizing the argument that we've just made, then we could look at a more general parabolic arc, say like this one, where you have 2 points, A prime and C prime. So we are able to calculate this area, and similarly, we'd be able to calculate this area, and then we can calculate the area of this triangle, because that's just a triangle. And so adding those 3 things, we'd be able to calculate the total area of that parabolic arc. And then we'd be able to compare that with the corresponding area of the maximal triangle contained in there, which is not going to be this one. It's going to be the one that you get by finding a tangent that's parallel to this one, or more simply, as the diagram in the previous page shows, another way of doing that would be to find the midpoint of this segment, wherever that is, and going down parallel to the axis. Go down parallel to the axis, you also find that maximal point for that triangle, as Archimedes understood. So there's a lot of interesting stuff here that we're going to want to do. We're actually want to roll up our sleeves and make some computations. And that's the heart of calculus. That's what calculus is all about. It's making computations. And so we're going to start doing that a little bit more. And we're going to now be focusing a little bit more in the direction of the worked problems. So a lot of this development, I want you to read about it in the worked problems, study that material, look at the diagrams carefully, follow the arguments. So the video is just a framework for this additional work that I'm going to be asking you to do, to look at, and then to do yourselves. So there's much to learn. I'm Norman Wildberger. Thanks for listening.